in this next subsection, we'll look at a blown up version of the symbol table that has additional operations, which are often useful and that binary search trees can also support. And this assumes that, like always in binary search trees, we assume that the keys have an order. We have to be able to tell everything on the left is smaller. Well, what does smaller mean? So the keys have some order. Then we can ask for the smallest or largest element, smallest or largest key in the symbol table. Or we can ask for what's the closest in this sense. If I have some key, what's the smallest that's bigger or the biggest that's smaller than a given key? So the neighboring ones. And the last two operations, these bring us back to this this claim I told you earlier that binary search trees are really like dynamic arrays. You can ask for the rank of an element, which is how many keys in the data structure are smaller. And you can ask for the so-and-so smallest, say the 10th smallest or the 100th smallest. And these two things together are really what an array can do. Specifically select. That's like selecting the ith element in an array. Just that now it's always the sorted array of all the elements that are currently in there. It's not that the elements get assigned some index and that index is fixed. The index is determined by what's currently stored in the data structure. So these two together give us this truly dynamic array in that sense, that you can access things by index, but you can also insert and delete at any point in time. This might be a good point to pick up on a question. So someone noted that Python doesn't actually have binary search trees. It's one of the very, very few languages that don't have a binary search tree implementation. But it does have dictionaries. And I told you that's the main way to implement dictionaries. There's one other big way, which are hash tables. We won't really cover that in this module. It's a lovely topic and worth knowing about. So I don't know, finding the appropriate videos on the resource page for this unit has all the infos about hash tables as well. So it's true, the dictionaries in Python are using a hash table. What hashing cannot easily support is the ordered symbol table operations that we're discussing right now. So if you need just a symbol table, hashing is often faster than binary search trees, but it has some additional assumptions. If you need the ordered operations, hashing is not really an option. All right. Yeah, some little practice to wake you up on this. This time I'll have to leave the slide on. Now, I mean, the point is not about memorizing the definition without having discussed it too much. So I wasn't very precise. The rank really is the number of keys that are strictly smaller. Okay? Many people. I'll leave you a minute. It's not a trick question. Okay, I think most people have voted, and so 4 is the correct answer. The easy way to work it out would be to exploit that I've drawn the BST as you always should. So you can just pretend that there's this array of the sorted keys. And so when 35 is here, there's 4 other keys to the left, and these are strictly smaller. That's one way. And we'll find a more algorithmic way on how to do this on binary search trees in a second. But basically, if you walk down this path to 35, you run along all the keys that are smaller in some way. The trick is we don't really want to visit them all and count them one by one. That would be fairly slow, right? If I asked you for 97, you would have to visit all the nodes in the tree. We don't want to do that. There's a nice trick that allows you to do this without visiting every node, and that's called an augmented binary search tree. So I'll just draw this like this. But what we really do is we have another field for each node where we store a number, and the number is the size of the subtree. How many keys are in this subtree, including the node? So all the leaves that have just null pointers have a 1. This one has a 2 because it's these two, then 4 for these two. 16 is because that's the size of the entire symbol table at this point. Okay? Now, how is that useful to answer these operations? Let's do our example from the question again. As always, we start with a search. So that's really the only thing I taught you about binary search trees. So what else should we do? Now, we can find 35 this way, but how can we work out the rank? How can we work out how many elements are to the left of it? And the trick here is that there's 2 types of nodes that are to the left, which I would say are skipped in that we continue working to the right and we leave them on the side. And they're skipped nodes. These are the nodes that we explicitly skip because they were smaller than the value we're looking for, and we visited them. Those are the nodes on the search path to the left of this line. Okay? So whenever we make this turn of the search path back to the right, that's one of these nodes that we skip, so we can count how many there are of these. But that's not all. We also have skipped subtrees. And these are the entire subtrees hanging left from the skipped nodes and from other nodes. But turns out that we always visit those. So we only have the left subtrees of the red nodes. So we have to skip all of these. In the tiny example, that's just a single node each. But you can easily imagine how this could be arbitrarily big. So how can we know how many we skipped? Well, luckily, the augmented search trees store the subtree sizes, so we can just add up all their subtree sizes. Okay? So in this case, we have a contribution of 2 red nodes skipped, and we have subtrees with total size 2 skipped. If you add up these 2 things, you arrive at 4, and that's the rank of 35. Okay? We also wanted to have a look at this opposite operation, select. So let's revisit what that means. I give you an index, I. The index should be like in an array, right? We start at 0 and n is excluded. But other than that, if you project the elements down, I want to access the ith element in the sorted array. Except that the array is not really there, it's just in my imagination, so I can't really use that. But that's the idea. So how can we select another obvious thing I should have stated, rank and select are opposites of each other. If I call rank of 35, I get back the index 4. And if I then say select 4, I should get back 35. That's the way in which they are inverses of each other. So let's use the same example and try to select the element at position 4. We start at 0, so it's the 5th smallest in a way. How do we do this? How do I know at the root whether I have to go left or right? I don't have a key. Oh my god, I'm screwed. Now, we do have a rank though, so we somehow have to find out if is the 4th smallest in the left or in the right subtree. And we know how big the left subtree is. It has 9 elements. That's plenty enough to cover position 4. All right? So we have to peek down into the left subtree to get its size. And then decide, yep, 9 is bigger than 4, so I can go to the left. I have to be careful that I'm starting with 1. So there's an offset here. I'm starting the index counting at 0, where subtree sizes, they count things, so they don't start at 0. But that tells me where to go, left or right. Same as before. Okay? Now I'm at this point, I'm still looking for the node with index 4 in this subtree. I can do the same. I can peek to the left and I notice, no, this is too small this time. There's only one node in there, but I'm looking for the 5th smallest. So this time I have to go to the right. Okay, I do go down here to peek at the size, and then I come back and decide, yeah, I have to go right. Now at this point, we cannot continue looking for the 4th smallest in this subtree. That wouldn't be the same as the 4th smallest overall, or position 4, 5th smallest. Oh. Why did I start counting at 0? We're trying to look for the position 4 in the global array, but now going to this subtree means we're cutting out this subrange of the array. So we have to adapt the rank that we're looking for. And how do we adapt? Same as before, we subtract 1 for the node that we skip because we visited it, and we subtract the size of this subtree because these are all the elements to the left of where I am now. Right, so here's the green one that I skip, here's the red one that I skip, and the green one, that's really the one from the subtree size, could be much bigger than a single element. Okay? So at this point, I have to look for the element at position 2 if I re-index this, right? Relative to this array, the indices have shifted. Clear? That's the only little trick where you have to be a bit careful. Then the rest is fairly straightforward. We look again. Peek down here. No, that's the wrong. 4 is big enough to find position 2, so I go there. Then I have again picture from before. I peek to the left. I find, no, that's not enough. There's not enough nodes in the left subtree, so I don't go there. Instead, I have to go right, but I have to subtract again. So here I'm looking for 2, and then -1 for this guy, and another -1 for the subtree that I'm skipping, which works out to 0, right? So in this case, we're looking for the node of position 0, which is the same as saying the leftmost in this subtree, because there's no left subtree. At this point, we found our 35. So there's a reason why I did select as the last operation. It's a little more cumbersome, or this is a little more tricky cases to distinguish because the rank we're looking for changes. But it follows really the same logic from before. You have to subtract things that you skipped. In rank, you have to add it. In select, you have to subtract it. Last little question. I kind of presented the solution to you before explaining why we don't do the obvious thing. If we want to have the ranks of elements, why don't we store the rank of each node? That sounds like the most obvious thing. It would certainly make rank and select much easier than the complicated procedure I've shown you. So why bother? The reason is we want to maintain this upon insertions and deletions. Remember, dynamic array. We don't care about static for this one. So if you kept the ranks, imagine there was a huge subtree over here, and you're inserting a new element here. The insertion of this new element was cheap, right? You just walk down 2 steps, stick the new node there. Suppose there was a null pointer before. But now suddenly the rank of all this huge bag of elements increases by 1 because there's one more smaller element. So there's really just no way we can update those in time proportional to the height of the tree. We would have to go to each and every single one of them and update their rank. That's not possible. Not without any, not without tricks that come out to be equivalent to what we're doing already. So there's always this little devil on my shoulder that says, you can't leave something that's not correctly in all, that's not true in all ways of understanding what you said. But we can't really update all those nodes. We would have to visit them all. So instead, we maintain something that's cheaper to maintain. We keep something that's cheaper to update. For the subtree sizes, that works because the subtree size is only something that looks downward in the tree. So for this red node, we would have a subtree size change for this one, and this one, and this one. But that happens to be exactly the nodes that we visit anyways on the search path. So we can stick a +1 in each of their subtree size fields while we're on our way to finding the node, doing the insertion. And similar for deletion. Okay? That's why the select procedure is a little more cumbersome to make, but it's the only way to keep that maintainable upon insertions and deletions.
Sorry, can you go back a slide?
Yep.
On the last slide, it says, what does this hate mean? Does it mean
Oh, it's the height again. Yeah.
Left subtree, or is it the whole binary tree overall?
It's just an upper bound. Okay, so in a way, the statement is a worst case statement. What it says is, okay, one step back. Big O of h means it's an upper bound. It's at most some constant times h asymptotically for sufficiently large n, ignoring constant factors, that kind of thing, right? Big O was this upper bound. So it could be cheaper sometimes. That's number one. If we're making such a statement without saying anything, it assumes the worst case. So it could be that the new insertion is the deepest down in the tree that it could possibly be. And so it could be that your specific insertion actually triggers as many changes as the tree is tall. Many other operations can be cheaper. Yeah, in this example, we would have 3 changes, whereas the tree could be much taller. Worst case, that would be the same.